With our lecture on organic reaction mechanisms, we are having this 32nd lecture on organic reaction mechanism, and it is our third lecture on nucleophilic aromatic substitution. In the earlier two lectures, we have discussed about SNAR mechanism and benzyne mechanism. And in this lecture today we will discuss about unimolecular mechanism, where this unimolecular mechanism can either take place by Srn1 mechanism or through some radical mechanism. As I have told you in the previous lectures that any reaction involving an aromatic ring where a nucleophile displaces a leaving group, that type of organic reaction is known as nucleophilic aromatic substitution reaction. And mainly these nucleophilic aromatic substitution reactions, they can be categorized into these four types. In the first two lectures we have already discussed about SNAR mechanism and benzyne mechanism. And in this third lecture we will discuss about these two types of mechanisms which are unimolecular in nature, and these mechanisms, they are Srn1 mechanism and Sn1 mechanism. As far as Srn1 mechanism is concerned, this is initiated by electron donors, whereas this Sn1 type of mechanism is more common in case of diazonium salts, where nucleophile is replaced with the nitrogen molecule. So we will discuss these two one by one. First is Srn1 mechanism. Now suppose we are having this type of substrate 5-iodo 1,2,4 trimethylbenzene, and if I treat this with strong base like potassium amide in liquid ammonia, that means at low temperature, then these two types of products, they can be formed. One product is where the nucleophile will get attached to the same carbon to which the leaving group was attached, and other addition is sine addition, where the nucleophile gets attached to carbon adjacent to where the leaving group was attached. So these two products, they are formed, B and C products, they are formed. But when the ratio of these products was seen, it was found that ratio of B to C was 0.63 to 1. That means this is formed in 0.63 if this is formed 1. So what we can see from here, that this type of product formation cannot take place by benzyne mechanism, because under benzyne mechanism also the aryl halides, under these conditions they are converted into these two types of products, but there the product ratio is 1:1. So because of this low product ratio between this and this, it is clear that here the mechanism involved is not the benzyne mechanism. Similarly, if we use an isomer of this A, that if this iodo group is attached to carbon 6 instead of carbon 5, that is 6-iodo 1,2,4 trimethyl benzene. That means then also we should get the same products, because then this product will be formed by substitution of the leaving group by amino group, same carbon, and this will be the adjacent carbon. So either we use 5-ido or 6-ido, we should get the same products. And when this reaction was performed, it was found that the ratio of formation of products again is different. Here the ratio of product formation is 5.9:1. So that means there is a change in the mechanism of this reaction when these types of substrates, ido substrates, they are involved. Whereas when instead of ido we use chloro or bromo, then the ratio was 1.46:1. So which is close to involving benzene mechanism. So in case of these types of ido substrates, a different mechanism is involved, and this mechanism is known as Srn1 mechanism. So here the proposed mechanism for Srn1 mechanism is that aryl iodide reacts with some electron donor, and this is converted into a radical anion, and then this radical anion breaks up into aryl cation and iodide ion. And then in the next step, this aryl cation interacts with the imide ion, and we will get an aniline radical anion. This aniline radical anion then again will react with one more molecule of the substrate, that is aryl iodide, and we will get the products, and this aryl iodide radical anion will be generated back, and this will follow a chain reaction. So this type of mechanism is a chain mechanism. So S is for substitution, R is for radical, N is for nucleophilic, and 1 is for unimolecular, because rate of reaction is dependent only on the concentration of the substrate and is independent of the concentration of the nucleophile. So that is why these types of mechanisms, they follow unimolecular mechanism. Then next is SN1 type of mechanism. Many of the aryl halides and sulfonates and even active ones, they rarely undergo SN1 type of mechanism. But in case of diazonium salts and aryl triflates, both of these types of substrates, they undergo this type of mechanism, which is SN1 type of mechanism, nucleophilic substitution unimolecular. So here the reaction is taking place in these two steps. For example, if this is the diazonium salt which we are having, in the first step this will undergo the elimination of a molecule of nitrogen, and phenyl cation will be formed, which is a slow process. So formation of phenyl cation, and if this phenyl group is a substituted one, we say aryl cation will be formed, is a slow process, and then this aryl or phenyl cation interacts with the nucleophile to give us the product. So nucleophilic substitution product is formed in this type in aryl diazonium salts, and because here this step is the slow step, that means this is the rate determining step, and that means in case of SN1 type of mechanism, rate of reaction will be dependent only on the concentration of the aryl diazonium salt. So that is why this is called as unimolecular nucleophilic substitution reaction. Now in case of SN1 type of mechanism, as I have told you, the different aryl cations, they are formed as intermediates, and evidence for existence of these as intermediate comes from the fact that first is that reaction is of first order and is independent of the concentration of the nucleophile. This is again because, as you have seen in the previous slide, the first step is the slowest step, where the diazonium salt breaks up into a aryl cation and a molecule of nitrogen is formed. So that is why the reaction is of first order. This is a direct evidence that Srn1 mechanism follows the unimolecular mechanism. Then second evidence is that when high concentration of halide salts are added, then the product is aryl halide, but rate is independent of the concentration of the added salt. So this is again an evidence which shows that mechanism follow unimolecular mechanism. Then if there are substituents present on the aromatic ring, then rates, they are consistent with the unimolecular rate determining cleavage, because in the first step the cleavage of the carbon nitrogen bond takes place in case of diazonium salts. So ring substituents, they will affect the rate of the reaction as is done in case of unimolecular rate determining cleavage steps. Then fourth evidence is that if we use deuterated compounds in the ortho position, then the substrates, they show secondary isotopic effects of the order of 1.22, and this high value of secondary isotopic effects can only be explained if there is a stabilization of the phenyl cation by hyperconjugation. For example, this one, if this is the phenyl cation, it undergo hyperconjugation and this type of benzene is formed, which is a stable intermediate, and H positive ions, they are formed. So this is again an evidence which tells us that Srn1 type of mechanism is being followed. Then another experiment was done, that was that the first step in the formation, the removal of nitrogen, to give us this is a reversible step. So this can be proved if we use this type of substrate in which one of the nitrogen is a N15 nitrogen. Now if this reaction is done in the first step, that means a molecule of nitrogen will be lost and we will get aryl cation, and if it is reversible, that means the nitrogen formed in the first step will interact with the aryl cation and we will get back the starting material. So when this reaction was performed, it was found that the recovered starting material contained not only the same substrate which we have started with, but it also gets this product also, where the N15 nitrogen is away from the aryl group, that is not directly bound to the carbon of the aryl group. So this proves that the first step is a reversible step. Then an additional evidence was also obtained when this type of substrate was treated with unlabeled nitrogen. So if this undergoes breaking of the bond, that means phenyl cation will be formed and a molecule of nitrogen will be formed, where one nitrogen is N14 and other is N15, whereas in the reaction mixture we are also having a nitrogen which is unlabeled. So when this reaction was done and we recovered a product where loss of 3% of the labeled nitrogen was there, which indicated that this on removal of nitrogen molecule exchanged with the atmospheric nitrogen which was present at the various 300 atmospheric pressure. So this also tells us that this mechanism, the first step is a reversible step. And this kinetic evidence and other evidence shows that step 1 changes from this state to a more complicated this type of tight ion molecular pair which is formed, and this ultimately dissociates to give us a molecule of nitrogen and a phenyl cation is formed. And this type of tight ion molecular pair has also been trapped with carbon monoxide. Then some examples which proves that the nucleophilic aromatic substitution takes place by unimolecular nucleophilic substitution mechanism. This can be seen from these two examples where this type of diazonium salt with HSO4 negative and PF6 negative. If you see the mechanism of this reaction, as we know that this will lose a molecule of nitrogen from here to give us a carbocation at this place, this type of carbocation is formed. Now here this positive charge on the aryl cation, this is located in a low energy sp2 hybrid sp2 atomic orbital, and there is no delocalization of this positive charge with the aromatic ring, and because of this intermediate is very unstable in nature. So you can say that aryl cations, they are very unstable intermediates. That's why they interact very easily with even the weakest of the nucleophiles. So water is a weak nucleophile. This attacks very easily to this positively charged intermediate to give us these types of products by Srn1 mechanism. Similarly, in this case also, this will lose a molecule of nitrogen, and this type of intermediate is formed. Again, positive charge in these cations is located in a low energy sp2 atomic orbital like this, and this nucleophile interacts very easily with this aryl cation to give us these types of product. Now we know that a greater amount of energy is required to generate these types of aryl cations, and this energy is provided because here the second product formed by elimination of this is a molecule of nitrogen, and the nitrogen which is formed is eliminated from the reaction mixture immediately, and when nitrogen has been eliminated from the reaction mixture, that means reversible step cannot take place. So this cannot reunite with the nitrogen. That is why this immediately interacts with whatsoever nucleophile is available to this positively charged body. So that is how the entire diazonium salt is gradually converted into the product by Srn1 type of mechanism. Now as I have told you, the aryl cation formed is a very strong electrophile which is very unstable in nature, and if this interacts with very weak nucleophiles. So if this weak nucleophile available is water, then we will get phenols as the product. But when the nucleophile is tetrafluoroborate or hexafluorophosphate, say in this case hexafluorophosphate, then this will interact with this nucleophile and we will get these types of aryl halides as the product, where we can substitute fluorine on the aromatic ring, which otherwise is a difficult process. So this formation of aryl fluorides through Srn1 mechanism is called as Srn reaction, and this is very important for the synthesis of aryl fluorides. Then in addition, the aryl diazonium salts, they can react with nucleophiles with some other mechanisms also. They most commonly used mechanisms, they are radical mechanism. So here what happens is that in the first step, aryl diazonium salts, they form radicals of this type, and these radicals then they lose molecular nitrogen, and an aryl radical is formed, and this aryl radical then reacts directly or indirectly with the nucleophile to give us different kinds of products. For example, say if aryl diazonium salts they react with copper chloride or copper bromide or copper cyanide, as we call these as Sandmeyer's reaction, we can synthesize aryl chlorides, aryl bromides or aryl cyanides respectively. Similarly, if these aryl diazonium salts they react with NaNO2 in copper 2 salts, we will get nitroarenes as the product, and if this reacts with H3PO2 in presence of copper 2, then we will get aromatic compounds, aromatic hydrocarbons as the product. The basic mechanism in these types of reaction where copper 1 is involved, so what happens is in the first step, aryl diazonium salts they react with copper 1 nucleophile, say this is copper 1, and nucleophile means either Cl or Br or Cl. So copper 1 nucleophile react with aryl diazonium salt. This copper 1 will change into copper 2, and we will get this type of radical, and then this radical will undergo dissociation to form a molecule of molecular nitrogen, and aryl free radical will be formed. Then this aryl free radical will react with this copper 2 plus nucleophilic salt formed, and this will form a complex with oxidation of copper 2 into copper 3. And then this aryl copper 3 nucleophile complex will undergo degradation to give us the product, and copper 1 nucleophile is generated back. So this is how these types of reactions through radical mechanism they can take place. Then this is another example of aryl diazonium salts, they react with potassium iodide. Now here the mechanism is, although product formed is same, that this will lose a molecule of nitrogen, and iodide ion as nucleophile get attached to this carbon, and we will get the product, but the mechanism of the reaction is different. So here the aryl diazonium salt will first react with this type of iodine radical anion. This iodine radical anion is formed in this way, that aryl diazonium salt will react with iodine negative from Ki, and we will get this type of radical formed, and iodide radical is also formed. Then this aryl this iodide radical formed will react with iodide ion, and we will get iodine radical anion from this place. So this iodine radical anion then will react with another molecule of aryl diazonium salt, and we will get this type of radical. Then this radical will lose nitrogen and aryl free radical is formed. Similarly, this will be converted into iodine, and this iodine will react with one molecule of Ki, and we will get I3 anion. This I3 anion will interact with aryl free radical, and we will get one iodide radical from here and aryl radical from here. They will form aryl iodide, and this radical anion of iodine will be generated back, and there will be a chain reaction which will consume all the substrate, and that will be converted into the product. So here also the unimolecular mechanism takes place by radical mechanism. So these are the two books which has been consulted for this lecture: Organic Reaction Mechanism by Jerry March and Advanced Organic Chemistry Reaction Mechanism by Brook. Thank you very much.